In this video, we're going to use the definition of the definite integral in order to find the value of the definite integral. Now, to remind you what that definition was, we have the limit of the Riemann sum as the lengths, or widths as we called them, of the subintervals approach zero. Or in particular, the mesh approaching zero, as long as we keep our subintervals the same length, we can, again, essentially look at the limit as n approaches infinity. And then each one of these terms we would consider as length times width of a certain rectangle. Now, before we can go through all the details of this, we need a few formulas, summation formulas, that will turn a summation into an expression in terms of the n, so we'll be able to take the limit as n approaches infinity. So here are the formulas that we will need. Make sure and write these down. You'll be using them throughout the worksheet with the definite integrals. Now I'm not going to explain where all of them come from, but let's just take a look at this top one. This is simply the definition of multiplication. If we have, say, 3 plus 3 plus 3 plus 3 plus 3, well, in technical terms, that would be the summation of 3. I goes from 1 up to 5. We have 5 terms of the constant 3, and, well, as I said, that's the definition of multiplying. We would take 3 times 5, and hopefully you know that's equal to 15. If you need to, pull out your calculators. Oh, you better not need to. But the constant times the number of numbers, and that's the formula we'll be using for the summation of a constant. Now, the summation of I squared, summation of I cubed, those are a little more, well, a lot more difficult to go through, and we're not going to do that at this time. But we will be using these, so make sure you write these down, have these available in working through the definite integrals using the definition. So, our definition of the definite integral, we will use that to integrate, to find the value of the integral from -1 to 2 of 4 minus x squared dx. Now, up to this point, all we've done with this notation is found the antiderivative. There have been no numbers here and here, but this turns out to be a different operation, and in a few days we'll actually see how this operation relates to the antiderivatives. Right now there's not really anything obvious about that, but we'll work our way up to that. But today we're going to calculate this value using this very formal definition, and a lot of steps to run through. The very first thing we need to look at is the interval. Well, we're going from -1 to 2. We need to partition the interval, and to do that, we've got to say, okay, how many rectangles, how many partitions are we going to split this into? And we have to use, in general, n parts. Okay. Well, as we did before, just put this up on the side, we were going from 0 to 2, and we used 4 rectangles. Well, what we ended up doing, we found our width, our delta x, as I'll call it, to be 1/2. Well, that's pretty easy to do with only 4 partitions going from 0 to 2, but let's see how a formula would find this as well. It depends on A and B and also N. And what we did, or what we could do to find delta x equals 1/2 is take B minus A over N, and see we'd have 2/4, or the value of 1/2. Well, this is what we need to do when we partition any interval into n parts. And we will definitely say, let's use equal widths, so all of the delta x sub i's will be equal. We can reduce that down to just delta x. And it's going to be calculated as B minus A over N. That is a very, very important formula for you to use. Write that down. Eventually you'll know it off the top of your head, but make sure that you have that written down. Okay, so delta x for our partition, B minus A. Now be careful here, it's B minus a -1 all over N. Well, we're not going to specify N at this point, so we just have to keep it as N. So we end up with delta x being the expression 3 divided by N, or 3 over N. Now to partition our interval from -1 to 2, I like to kind of just think about the number line starting at -1, ending at 2, or again in general, -1 we could say is x sub 0, or the a value as we talked about earlier, and then x sub 1. How do we calculate x sub 1? Well, remember what we did on this. We started at 0. X sub 1 ended up being 1/2 because we went 0 plus the delta x. So if we do that in this partition, from -1 out to x sub 1, x sub 1 will be represented as what? Well, starting at -1 plus delta x, because the width of this subinterval will be delta x. So x sub 1 we could say is -1 plus 3 over N. Next, what about x sub 2? Well, to get from x sub 1 to x sub 2, we go another delta x. So x sub 2 is going to be, well, to represent that in this case, we would say starts at -1, and we're adding, starting here, we're adding, well, there's one delta x and there's a second delta x. Or, in particular, x sub 2 would be -1 plus 2 times the delta x for this problem, which is 3 over N. Well, let's keep going. We'll do one more here and then try to generalize it. From x sub 2 to x sub 3, we have one more delta x. So x sub 3 would be, well, once again, starting at -1, we're going how many delta x's? Well, we get 3 delta x's. So x sub 3 is going to be negative 1 plus 3 times the delta x representation. Now, are you maybe seeing a pattern here? Look at our subscripts, x sub 1, negative 1 plus 3 over n. X sub 2, negative 1 plus 2 times 3 over n. X sub 3, negative 1 plus 3 times 3 over n. We're going to be generalizing this, saying if we let x sub I be our partition, maybe it's x sub 10, maybe it's x sub 55, but x sub I would be represented by what? Well, as with all of these previously, we start out with negative 1 plus, well, how many delta x's are we adding to get to that? It's going to be the I value, whatever x sub I part we're at, times the delta x. And let's even back up a little further. Here we're saying negative 1 plus I times the 3 over n. X sub I in general, no matter what we're dealing with here, we're starting at A and we're adding so many of the delta x's. If you can keep that in mind, that is a quick shortcut in getting what x sub I represents. Now, this becomes very important because the partitions, the x values, are what we input into the function to give us the idea of the height of the rectangle. So the height of the rectangle, or length, times width, which is our delta x. Basically is showing how we would estimate the area under this curve. Now, what we're choosing here, we're choosing x sub 1 to be the sampling point of the first rectangle. Or in this case, what we've talked about before, we use x sub 1, the right endpoint, to calculate the length of the rectangle. If we drew our picture of the function and drew some rectangles, the height of the rectangle would be dependent on what the function value is, the y value for that particular x value. And that is saying the right endpoints, as we talked about before. Once again, with the widths being the same, we don't need to specify delta x sub 1, delta x sub 2. We can just say, in general, delta x. So because of the equivalency of our delta x, we can factor that out. So our summation for the approximation of the area, this would be the sum of all the heights times that delta x. We're factoring out all the delta x's since they are the same value. And this would be the approximation. This is what we used before, using 4 rectangles or 8 rectangles. This is precisely the operations we did. But now, let's take a look at what the function is. In our example, we are looking at the definite integral from negative 1 to 2 of the function 4 minus x squared. So we're going to be inputting these x values into this function. Well, to represent the right endpoints as our sampling point, plugging in the x value into the function, we are actually using x sub I, the first subinterval, or when I equals 1, we're going to use f of x sub 1. The second subinterval, okay, we will use x sub 2 as our sampling point. So we are using the right endpoint for each one of these sampling points, and ultimately we could rewrite our function then, our sum, as f of x sub I. Okay, in general, we're summing this up, so we're saying the summation I goes from 1 to n of f of x sub I. That right there is precisely what we've written right here. And I've stated this, but let's write this down. Right endpoint for each of these subintervals is represented by x sub I. Now, we don't have to use the right endpoint. We could use the left endpoint, but the right endpoint is going to be so much easier to deal with. Okay. By the way, the left endpoint would actually be represented by x sub I minus 1. So that's why we want to choose the right endpoint, x sub I. We've already got x sub I represented. We just have to input it into the function. So f of x sub I, that summation, times, don't forget times our delta x. Now, ultimately, as we calculate this definite integral, we've got to take the limit of all this stuff as the mesh approaches 0. Well, the mesh, let's go ahead and talk about that right now. The mesh, or the norm, because we chose all of the widths of our subintervals to be equal, the largest one will be the same as every one of them, and that's going to be delta x. And in this particular case, our definite integral, we calculated that to be 3 over n. Okay. Well, as the mesh approaches 0, we would have 3 over n approaching 0, which we can translate that as n must approach infinity. If we end up with n in the denominator and some constant in the numerator, as n approaches infinity, that will approach 0. So we have now transformed our definition because we have kept all of the widths equal. We can now say take the limit as n approaches infinity for our summation I going from 1 to n of, well, let's look at what this would be. We said x sub I up here at the top. We determined that is to be -1 plus I times 3 over n, and then we multiply that by delta x. Now, one more calculation. In particular, we need to input our x sub I into our function, 4 minus x squared, and then we'll have our summation to calculate. So we're ready to show what this represents based on our function 4 minus x squared. So our input, we take 4 minus our input squared. Lots of parentheses here. And then algebraically, we have a few things to do to calculate this. So we'll need to multiply all that out. Don't forget, this is minus that entire quantity. So FOIL, make sure you watch your signs. And we get this expression, then multiplying the negative through. Our function value then would be 3 plus, well, let's go ahead and make this I times 6 over n minus I squared times 9 over n squared. So that expression will go into our summation formula there, and we'll have limit as n approaches infinity, the summation from 1 to n of 3 plus I times 6 over n. Let's go ahead and put it this way, a little more typical way of writing the summation. And then don't forget times the delta x, which is our 3 over n. Now, we're not going to worry about the limit right now. We're going to look at some summation properties to be able to use those summation formulas we looked at earlier. First of all, the summation properties, anytime we're adding or subtracting inside a summation, we can go ahead and separate those into individual summations. So we can say the sum of 3 plus the sum of 6 over n times I minus the sum of 9 over n squared times I squared. Now, all we're worrying about right now is this. We'll need to remember to multiply that result by the 3 over n and then take the limit, but we've got a ways to go before we get there. And one final property that will be helpful, anytime we have a constant times our index, we can rewrite that as, it's kind of like factoring out the constant. So we still have our summation of 3, but the second summation we can write as 6 over n times the summation of I. Now, this was the formula, one of the formulas we looked at the very beginning of this video. And then the last term we can factor out the 9 over n squared, and we have the summation of I squared, which was another formula from our list that we started the video with. So at this point, we're ready to change all of these summations into those formulas. Well, at this point, we will recall our summation formulas, and the 3 formulas that we will need for this problem are listed here, and we'll proceed with our problem and see how we use those, in what manner, and then we will also see lots of algebra. It's not really the calculus that's hard, it's that pesky old algebra. So with the expression we have at this point, we've got the sum of a constant, so 3 times n will be the result of that first summation formula. The second summation, we have the 6 over n times the summation of I. So the formula there, n times the quantity n plus 1 all over 2. And then finally our summation of I squared times our 9 over n squared. So we'll have n times the quantity n plus 1 times the quantity 2n plus 1 all over 6. And this will now turn all of the summations into terms of just n. And remember, this is not the entire limit that we're looking for. This was the function of our c sub I, function of our sampling point, which was x sub I. And this now can be combined. Well, we've got a lot of simplifying we can do here, but if we put this back into our limit formula, we end up with this expression. Now we're taking the limit of f of c sub I, or the f of x sub I we came up with, times, don't forget our delta x was the 3 over n. So back to the entire expression. Now we're going to have one huge limit to, well, simplify algebraically, and then finally do a little bit of calculus as we apply n approaches infinity. So let's continue simplifying. Looks like as we move to this part, n divided by n will cancel. 2 goes into 6, leaving us 3 times there. So let's kind of make little notes as we go here. So far we've got those simplified. And then this last part gets a little more involved. N divided by n squared leaves us with an n in the denominator. 9 divided by 6, well, we'll have 3 over 2 once we simplify that. Now we start canceling things, we can easily lose them, so don't lose these values in the overall expression. And the big algebraic thing for this expression is multiplying this out and then combining it with the rest of it. So we can kind of combine what we've done so far, minus 3 over 2n, and then times the binomials multiplied together, 2n squared plus n plus 2n would give us 3n plus 1. Okay. Now again, that's only what we're doing within this. We can simplify greatly still before we even multiply the 3 over n. So we'll have 3n plus 3n plus 3, and then minus, make sure we subtract every term here, 3 over 2n times 2n squared would leave us with minus 3n. 2's would cancel and one of the n's would cancel. Then multiplying it by 3n, we'll have the minus 9 over 2 with the n's canceling in those spots, and then minus, well, thankfully times 1, we get the minus 3 over 2n for that expression. And let's see, we can still do some simplifying. We've got 3n minus 3n. Well, that's going to leave us a 3n for that part. 3 minus 9 halves would be, well, 6 halves minus 9 halves. We'll have a minus 3 halves there. And finally, the minus 3 over 2n. Again, all of that has been simplified from this. So now we've got the limit as n approaches infinity of this times 3 over n. Okay, multiplying our delta x by all this. So, almost done. Limit as n approaches infinity. Now we multiply this through the parentheses. And 3n times 3 over n will leave us with 9 minus 9 over 2n and minus 9 over 2n squared. Well, thankfully we're having n approach infinity, and with the n's in the denominators here and here, both of those terms will go to 0. So this limit equals 9. So what have we done here? Through all of this long and drawn out procedure, remember what our original problem was? Integral from -1 to 2 of 4 minus x squared dx. Through all this process, we get an answer of 9. Now we're going to be looking at what that value of 9 can represent, but technically this is the operation, it's a mathematical operation of the definite integral. And also, thankfully, we'll be able to find some shortcuts in doing this, but this is finding this definite integral, the value of that, using the definition of the definite integral.